Okay, very good. So first of all, about logistics, just want to tell to all the students, you should monitor the announcement page on Brightspace, and so we will put every communication there. And apart from that, so today I'm very happy to have Roger Shell as a speaker, and he's now president and founder of AESEC Corporation, and he has been referred as the father of trusted computer systems. And today he will talk about how to reduce the attack surface in cyber physical systems.
Well, thank you. Appreciate that, Antonio.
Thank you.
I want to thank Purdue for the opportunity to talk to the class and those others that chime in. I've always enjoyed the interactions with the classroom. And although I can't see them face to face, I know you're there, students. So it's a real privilege for me. My name is Roger Shell, and as Antonio mentioned, I'm the president of AESEC Corporation, and our primary business is as a vendor of a verifiably secure operating system that is called GemSauce. And so that's what I'm here to show about how that can be used. We believe in some of the work we've done in the last few years. We've spent actually several years working to illustrate how that secure operating system makes a difference for producing secure control systems. And it's certainly not the whole control system, but we think in terms of the attack surface, we can actually reduce the attack surface for the overall control system, as I want to describe. The differentiation, I think, of our approach to operating systems, and it's not just exclusively us, but we build an operating system that's secure by construction, which is unusual in today's practice. The usual practice today is a paradigm that I would call secure by test and analysis, more pejoratively penetrate and patch. And this, we think, has not worked all that well. You just read the newspapers. And the difference is that of the systems that have been done as security by construction, these have run for decades in the face of nation-state adversaries and have never had a reported security patch. And some of you students may raise your eyebrows a bit and you say, okay, an operating system that never has a security patch? Well, that's not what we've always been told. The common myth is that in terms of an attack to your system, it's not when you're going to get hacked, and not how, or if, it's when. Well, that's not true. We can do much better than that. And so I want to talk about that today and give you a sense for what security by construction is, not in detail, and why that's significant to control systems. The outline for what I want to talk about today is the problem. We won't spend much time on that. It's generally fairly widely recognized, but it's been described as a national existential risk. And I'll spend most of the time talking about how we can use a secure operating system, a trustworthy operating system, to produce a reusable, trusted device on which control systems can be built. And then we'll wrap up with a few comments about how that trusted device can be used by people that are actually producing commercial products that we don't ourselves produce, like control systems, PLCs. So we'll start with the problem, national existential risk, and a couple of parts of that problem we'll emphasize. The problem largely comes about because the cyber physical systems, the actual physical devices in the control systems, are just simply not resilient to cyber attack. And so you end up with a vulnerability being exposed by critical cyber-physical components. And as an illustration of that, there are a lot of control systems that are out there, but a common one is the bulk power generation system. And a illustration of that are things like the major power generators or the transformers or things like that. And so that's what people believe causes an existential risk. That has been characterized by others in terms of the impact. Leon Panetta, Secretary Panetta, was previously Secretary of Defense and CIA Director. And he said about a year or so ago that his biggest nightmare is an attack that disables the U.S. infrastructure for particular power. And in his opinion, that could result in millions of lost lives. And I must say that that estimate is certainly not outlandish as what I see a lot of other people talk about. Now, just be aware that there are people out there, people have published things recently that said, well, this really is overhyped. You know, we don't see a lot of societies being crashed by this. We don't think this problem in terms of the power grid and such is really real. So they're in the minority, and they don't have a much in their argument for their favor. So not being the expert myself, we will go with the majority opinion, which seems to be, with good support, that it is an actual existential risk. Recently, the president issued an executive order, and he declared that there's a national emergency with regard to the security of the U.S. bulk power system. A commission within the last month issued a report and observed that the original equipment manufacturers, those who produce these cyber-physical devices, are targets for malware. So that malware can lie in wait and be activated later, which is why we don't see it being exercised every day. And that the people that are mounting these cyber threats are certainly spending major money to invest in the ability to conduct an attack against control systems. Some of you may have seen recently the press reports of an attack by a Russian visitor that offered $1 million to a Tesla employee in order to attack and plant malware in their system. And the comment was that he expected that they would be able to extract $4 million in terms of the results of that attack. So there is some basis for the opinion, since this is a risk. The Washington Post reporting on that report said that Russia has caused physical damage already from afar. There are instances of this. And they said that they believe that China has already implanted malware in various of these control systems. Too late, they thought, to get do anything about that. Well, as we will see today, it's actually not too late. We can actually go back and restrict the ability of those to cause damage. So what is this problem that we're concerned with? Well, the problem is there are physical devices that are critical components in our critical infrastructure. Now, these devices can be attacked by cyber. And the root cause of these attacks is that those computer systems all use an operating system, which is not a trustworthy operating system. Things like programmable logic controllers, which are an example of a control system. And if you don't have a trustworthy operating system, NIST published a guideline that I'll mention again later that points out that it's scientifically impossible to build a secure system without a trustworthy operating system. Just simply a scientific impossibility. And yet, The truth is that essentially all current commercial operating systems use untrustworthy all PLCs use untrustworthy operating systems. The reality is that there are today only a handful of common operating systems that are used by control systems, and none of those are trustworthy. And what is the evidence they're not trustworthy? Well, you've got a stream of regular security patches. In fact, for some operating systems, they're so frequently that they have been memorialized as Patch Tuesday, in which at least once a month you expect a bunch of security patches. And those cyber attacks can inflict permanent physical damage. We see evidence of that. Some of you will have heard of the Stuxnet attack, allegedly by Israel and the United States against the Iranian enrichment centrifuges. They destroyed a major portion of their centrifuge capability by cyber attack. Crash override was another attack you may have read about that attacked physically the Ukrainian grid. And the Triton is another attack which aimed to destroy significant parts of the Saudi refinery capability. So it is not just a myth that cyber attack can in fact cause physical damage. As preventing that physical damage to critical devices is really the focus of what I want to talk about today. So how are we going to do that? Well, the key, we believe, is to have a secure operating system embedded in what we call a reusable trusted device. That trusted device you can think of as a motherboard that could go in a PLC or a control system. It could be a system on a chip that is used various forms, but there's a hardware software device that can be run the application. The primary technology for doing a secure operating system is something that has been known for some 40 years as security kernel technology. And that technology includes the ability to define and enforce different domains on the applications that run on the operating system, and in particular for integrity. And it's commonly known as the mandatory access control. You'll find that term. You take various kind of courses about cybersecurity, and you'll find references to it. The military sometimes refers to it as multi-level security, but it is a key capability of a verifiably secure operating system. To demonstrate how that can help with control systems, we've used an open PLC system and put them on our GemSauce operating system product in order to demonstrate how that can be leveraged for control systems, and to demonstrate how it can provide mature subversion mitigation. That's what we're going to talk about. Those are the four major points. First, the security kernel technology. Some of you may have heard of it, some may not. The term kernel has been much misused since that time, but it was first introduced in 1972 as a compact kernel of an operating system and the supporting hardware, such that an antagonist could provide the remainder of the system, like a PLC, like other sort of control system capabilities, without compromising the protection provided. It was later summarized a decade later in an IEEE article. It was noted that one of its distinctive factors was that it can be designed to address, security by construction, if you will, attacks that the designers never considered. Now, this is not commonly what is taught for cybersecurity. The common point of view is, well, you go out and you find out what the attacks are, then you design a defense against that attack, then you wait for the next attack, and then you define a defense against that attack, and it never ends. You don't know where it ends. And that leads to the belief that it's not if you will be subverted, it's that when. That's not what the security kernel provides. It provides defense against attacks that the designers never even considered. They say, well, that's a pipe dream. Does that really work? Well, it turns out that there have been a half a dozen security kernel-based systems that ran for years, even decades. Very high profile, things like the Pentagon, in the face of nation-state adversaries without ever a single reported security patch. Now, that's not something you'll find for any of that handful of operating systems that are used in the control system. None of them can say they've run for decades without a reported security patch. That's what's different about security by instruction. Now, has this been looked at? Well, it turns out that back in the 1970s, ARPA had a review group, and ARPA had people that said, this is really too good to be true. We can't believe you can't have an operating system that never has a security patch. Just can't be. So they brought in this group headed by Butler Lanson, and they expected that what they were going to do is debunk this false claim that you could build that. The report the group came out with is not what they expected. They said the only way we know to build highly secure software systems of any practical interest is a kernel approach. And that's still true today. And that was subsequently codified, that approach, by NSA into something called the Trusted Computer System Evaluation Criteria, informally known as the Orange Book, something called Class A1. And I'll be referring to that several times because that really is the codification of what it takes to build a security kernel. Now, the glossary of that Orange Book defines a security kernel as the hardware, firmware, and software that implement the reference monitor concept. Now, we've taken that and noted that you're talking about the hardware, firmware, and software elements, and we're packaging that into a physical device that we call a reusable trusted device. And that will be what I'll talk about several times a day as the instantiation of a security kernel that we think is important for a control system. Now, how do you build one of those? Well, you start with a typical hardware platform. Hardware has to have some capabilities to support security. Things called segmentation and rings are the primary ones. It has network interfaces, interface to communicate, storage, that sort of thing. You put on top of that hardware the security kernel software that's been designed to meet the Class A1. And that package, think of it as a motherboard in some cases, is what we call a reusable trusted device. Now, on top of that usable trusted device, you then put applications, which can include control system applications like programmable logic controllers. And that'll be our illustration today of the control system. And this is truly a paradigm shift. No Class A1 security system has ever had a reported security patch in over decades of use in the face of national state adversaries. That's just not the paradigm that people are generally working with today. Why does it matter? Well, we'll look at why that matters, what difference that makes. A VP of risk management at Union Pacific several years ago said, after he considered this in their control system, said, a trusted operating system changes everything. You approach the design process very much differently if you know that you can have a truly trustworthy operating system. And we want to illustrate today how that can be done. I hope you will find it interesting. So the approach has three major pieces. First, that operating system has to have control sharing between integrity domains. It has to enforce the MAC control policies. Nothing else can affect it. The operating system does that, the kernel. Then you have to be able to verify that design of the MAC enforcement. And as I noted before, the security by test and analysis has consistently failed over the years. And in fact, it will never finish because you don't know when you're done. In contrast, and we'll talk a little bit more about how to do security by instruction, and those have been successful over decades. And what that means, what do you have to do to build one, is codified in the Class A1 approach. And finally, that security kernel technology has to provide the mitigation of subversion, which is also embodied in the Class A1 codification. You have to have all three of those things to have a secure operating system. That has sometimes been called the defense triad. I referred to it that way in a paper I wrote for the Communications AHCM a couple of years ago. Basically, these things, the MAC policy, it's enforced, a reference monitor implementation, known as the security kernel, and the dealing with subversion. Now, how are we going to deal with the mandatory access control? How can we actually separate those integrity domains so that I can't have a low integrity things impacting high integrity, which is what the definition of the security kernel says, that whatever you put on top of the operating system can't subvert the controls of the security. Well, the NIST has published a document on trustworthy secure system development, their flagship document on security engineering. And that has an appendix F that deals substantially with the reference monitor concept. It's an abstraction of a security model that is necessary and sufficient to enforce access controls. Necessary and sufficient to enforce the access controls. It doesn't depend on things outside the reference monitor implemented as security kernel, which is defined as implementation. And the particular application of the mandatory access controls that we will use in the PLC case is for integrity, protecting low integrity items from accessing high integrity. Now, what do we mean security by construction? Well, Class A1 defines what that means. It says you have to know what you want to do to start with. You have to have a security policy. That's what the mandatory access control policy is about. It says that the domains of the policy can be organized into a mathematical lattice, and that provides a mathematical basis for describing the relationships that exist between high integrity and low integrity. And it says you have to take that, and according to Class A1, you have to write that down in a formal security model, a formal security policy model. That is really the linchpin of security by construction. As you've got a model, by formal, I mean you have actual mathematical proofs that says that for all possible applications running on such security code, you can never have a low integrity execution impact a high integrity domain. That's a proof, QED at the end. The formal security policy model is the key to doing that. And it essentially defines at an abstract level, in a mathematical model, the security kernel API. You then translate that API, and find an instance of it, as a formal top-level specification, to our development specification. It describes the API precisely as you would expect an API to be described for a security kernel or an operating system. And then you have to have a set of design implementation. So you have to have source code that actually implements that API. And there's a set of constraints as to how you have to build that implementation. Actually, the A1 criteria, when it was evaluated by NSA in the UK and in Germany, they had something like 25 different factors. You had to meet all of those factors in order to satisfy the requirement as implementation of the reference monitor. And it had things like information hiding and layering and code correspondence to show that every piece of code actually is reflected in the formal top-level specification. And then from that source code, you actually produce the end product, the binaries. And you have to have with that, for a secure system, a user guide, how do you use it, how the applications call it, a trusted facility manual, how do you administer it, and you have to have with it an ability to provide trusted distribution of updates to the system. You want to add new features, capabilities, you need to be able to distribute that securely. And you need to be able to distribute securely the applications that run on it. In order to do that, you have to have the hardware support, and the A1 requires that you actually reflect in your formal specification, formal top-level specification, the hardware controls to provide things like hardware segmentation that are essential, and those have to be reflected in that top-level specification. And that's a process you go through. I don't claim that you will have understood all the details. When I was on the faculty of USC, I taught a 3-semester sequence of courses, which were primarily about what do you need to know and how to do security by construction. This is a very brief overview of that 3-semester sequence of courses. I'll just note that I talk about verifiable design, and you will see people using that term verifiable in various ways today, or using a kernel in various ways, which doesn't mean the same thing. They're attempts to shortcut the hard work. A reference monitor implementation and a formal security policy model are long, hard work. It has never been accomplished in less than 10 to 15 years. And so the unwary or lazy look for plausible shortcuts. And I'll just list some of them here. There are lots of others. But people have talked about a verifiable operating system. The example goes by the acronym SEL4. But it has no formal security policy model, does not have a verification that satisfies any policy. It simply is functional verification. A much, much easier job, and yes, they avoided the work. They don't really talk about avoiding the work. Another approach to this was a system called MILS. They actually explicitly said, MILS does not include a reference monitor. That's outside their partition kernel, and it doesn't have a formal security policy model. Others have said, well, we'll just have verified hardware, and we don't have to have a formal security policy model for that. We'll just say, here's what our hardware does. And things like the DARPA crash and Cherry are examples of that. It's not bad research. It's not wrong in its claims. It just doesn't provide verifiably secure with regard to the mandatory access control. Others have proposed things like static code analysis, but they lack the policy models too. Bottom line is that none of those shortcuts can enforce with an integrity MAC or something like a PLC. They simply are shortcuts that may be useful in some contexts, but they don't allow you to do what we're talking about in terms of integrity MAC. So we'll say no more about that. Just be aware that you will see these claims for kernels and verifiable operating systems that are just not talking about the same goal. So what's our goal in terms of the integrity MAC? Well, we start out with a physical device, then a power generator, or a large transformer. And now, what has happened for several decades now, we connect that to the internet, to public networks. Well, what stands between anybody that can access a public network and that physical device? Well, there have been various demonstrations. One project you will find in the literature called the Aurora Project, in which somebody showed how in accessing over the internet, I can in fact destroy physically a large power generator. So people have said, well, what we ought to do is we ought to have a private network, a separate internet that we're going to use for the power grid. And you can do that, and they essentially do that, and they have a separate domain in which they say, now, the only thing that's inside my distributed control is just the power grid network. Well, with our approach of a reusable trusted device, we're going to implement that same notion of a different integrity domain, but we're going to do it without the need for a separate internet. And some people say, well, I don't need everything about that control system separate. I just need to separate the control part. That's the stuff that is physically telling the device what to do, the so-called SCADA. And so they said, we'll just have a separate control network, SCADA, to do that. Well, yes, there is a very strong need that the programmable logic, the logic that actually controls the physical device, has to be secure, but that itself is a fairly large body of code, and you can't have that verifiably secure either. So our approach is to say, well, there's a much smaller part of that we can define that just provides the cyber physical control. So the only thing that actually sends the electrical signals to the physical device is in that cyber physical control system. NIST actually calls out this kind of capability in their same flagship document regarding the electric grid, and they note the value, what they call a highly assured kernel-based operating system in programmable logic controllers. That's exactly what we're talking about, is implementing that strategy that NIST called out. And then they go on to point out that that actually controls the flow of information between different integrity domains, which is the goal. How do I keep low integrity things from impacting the high integrity domains? We've implemented that by taking an example of a PLC, open PLC, just a research demonstration. Put that on top of our GemSauce operating system and hardware. And what you see reflected here is that we've got this cybersecurity domain. That's one of the high security domains. It runs in a couple of different processes, and it has a separate domain, the SCADA domain, a separate domain, distributed control, separate domain, the public networks that we just looked at. But the operating system down below, the security kernel in GemSauce, actually ensures the integrity between those domains, from the most critical to the least critical. There are some essential hardware properties that Class A1 spells out for doing that. You need to have hardware rings, more than 2, because you have to separate the operating system from the application, and the operating system services from the kernel. You also have to have memory segmentation, not paging, but memory segmentation in the hardware. It's the only way that we've ever known how to build a security kernel. And those are the things that are there. You also have to have a strong process model. And all of those are available in contemporary hardware. In fact, this picture I show here is right from the Intel processor manual for their x86 architecture that is still in all their major processors today. So this is the research vehicle on top of which we have implemented what I'm describing as a verifiable PLC. Our demonstration approach is to take those 4 distinct hierarchical integrity domains and to implement them on top of the security kernel, the reusable trusted device. Those are the cyber physical control, the most secure. The supervisory, the SCADA domain, that contains what's commonly known in PLCs as the main logic loop. It's called that because it's a programmable logic controller. It is actually an implementation of what engineers like me, trained as electrical engineer, used to build in circuits that would actually control the devices. Today, that's done through a programmable logic controller. And we have on top of that network interfaces and obviously the untrusted network. Now, people for years have said, but control systems are fundamentally different than IT. They're absolutely right. They say, you guys can talk about the security kernel and operating systems for IT, but that doesn't work for control systems. That's been a myth that's been around for a long time. You can find a lot of people. You go to the control system arena, and a lot of people will say, control systems are fundamentally different. You can't use that stuff that you use for IT systems and control systems. Well, that's true. You can't use the stuff that's used for IT, which is penetrate and patch, doesn't work. But we've taken an open PLC to say, what can you do with that? Came out of the University of Alabama. It's a highly functional PLC for Windows and Linux, and some commercial vendors are even using it. We even have one installed as a research illustration on Matt Bishop's UC Davis Security Lab on a GemSauce a developer's kit is what's in our product. And so this is a basis. We're not just hypothesizing about what a PLC might do, although it's taken us a couple of years to do this. We've actually taken a running PLC research product and we put that on it. Then we can put that PLC, and this is a diagram that's right from the open PLC that says here's the pieces. We've just separated those, we've deconstructed those into the 4 domains I've talked about. The most critical one, of course, is the cyber physical domain. That's one illustrated here on the far left. And we then have in it the code that's executing in the medium integrity, the SCADA code, the others, are code right from the open source PLC. We didn't recode those systems. We simply took their code and moved that and refactored it to run onto GemSauce. Not trivial, but not rocket science. Now, what are we talking about in terms of the attack surfaces that those domains represent? Well, just as an illustration, I said, well, let's go out and look at the public networks. Order of easily way more than 5 million bytes of code in public network code out there. This is an amazing attack surface for the attacker. But I can reduce that down, so I'm doing now just I have to attack the distributed control system. That gets rid of a lot of the attack surface. That distributed control is only like 3% of the total. And now I've only left with this SCADA, that logic loop, this programmable logic that engineers wrote. Still a fairly large amount of things, over 1 billion bytes implemented in the open PLC, 20% of the total. So I'm reducing down, but still a lot. But if I get the cyber physical controls, the things that are there, the things that can only control the hardware, that's less than 1%. Mind you, less than 1% of the total attack surface that an attacker today is where he has to attack if he's going to be able to successfully subvert a verifiable PLC. Well, that's how we're talking about reducing the attack surface. Now, that attack surface has to include dealing with subversion. And again, then this flagship document says that highly trustworthy components have to be resistant to penetration from determined adversaries. And it goes further that the Class A1 codification I talked about is distinguished from other criteria by substantially dealing with the problem of subversion of the security mechanism. And that's what you have to use. Nothing else will do. So what is it that deals with subversion? Well, there's a list of things, but you have to get trusted boot. It starts up. You have to know the devices that you're on. You have to know their properties. You have to have code correspondence to stop dead code. But every line of code that's inside the trusted system has to be mappable in the operating system to the top level specification. I have to have trusted distribution. I have to be able to make GemSauce. I have to be able to distribute updates to GemSauce over the internet, available to any attacker, and have them securely installed without an attack. NSA evaluated that as part of what they demonstrated that GemSauce as a Class A1 system could resist. And you have to have media integrity. I can't just have a USB drive that I found in the parking lot that I can plug in and subvert the whole system. So if I apply that to something like Stuxnet, I say, well, that, what do I do? Well, I have to both protect the vendor, like ESIC provides a trusted distribution of GemSauce, and it's provided to a supplier like Siemens who does a PLC, and they can provide updates. That's all part of what's necessary and sufficient to protect the physical device. So that leaves you with a question. So how can I get that into systems that the PLC vendor can sell? Well, the system is a traditional OEM, original equipment manufacturer model that's used for almost everything you buy IT. The vendor offers the trusted device. The OEM produces the platform. something called value-added resellers package that, and solution providers integrate that into a system. The trusted device provider for the vendor, as I mentioned, typically takes 10 to 15 years to build. It's never been done less than that. But actually getting that out to the deployment can be done in 2 to 3 years. This was noted by a previous director of NSA, the most knowledgeable in cyber in my view, who said that this is a very high probability or high priority problem. He's concerned about subversion. But he said the demands that the first set of solutions are built on platforms which NSA previously evaluated Class A1. That's the only practical way to deploy in a couple of years. He was right, we believe. That's why we propose to use that approach. So, in summary, the problem, we accept the experts and say this is a national existential risk. We believe that the Class A1 is a way of just a criteria in detail of how to build a reusable trusted device, hardware and software. And the standard way of vendors delivering their stuff to the marketplace, the OEM model, provides for commercialization of that. So, what do you need? The bottom line, you have to recognize there are critical physical components. The kernel makes the cyber physical system attack surface much smaller, 1% of that without it. The PLC functionality and performance is preserved because they run on that trusted operating system. And the mature business model that's out there gives a way to get that to the marketplace. So the experts say we have a clear need. We agree. The commercial technology exists. Been run systems designed to meet Class A1 have been successfully deployed for decades without a security patch. What we don't have is PLC manufacturers and other control systems have not adopted that in their products. That's something that you as students go out and you can help them understand the value of this, and some of the others who are listening into this call and say, that's the next step. That's the remaining step. We can't have a complete chain to deliver that solution to the marketplace without the involvement of those PLC manufacturers. They do not have to become kernel experts. They do not have to become builders, but they have to build their PLCs on a verifiably secure operating system. That's what I thought was an opportunity to help you understand a little bit what we mean when we say we can dramatically reduce the attack surface for control systems. At this point, some of you may have produced some questions, and I'll go back to the panel and see what we have.
Thanks, Roger. That was really a great discussion. I do have a couple things that look like they've shown up. The first question I see is, why don't more OS developers use a security kernel approach? Too expensive? Takes too long? Flexibility?
We've asked that question. We've talked to a number of the major producers, and the answer has always been the same. There's not a market. Nobody's willing to pay for it. One of the major technology people that you would know, as I reported in an interview several years ago, I sat in his office, he shook his finger in my face, and he said, the path is littered with the corpses of those who think the government cares about security. He said, I don't intend to join them. And I said, what would it take to convince you? Well, he said, for a starting point, he said, I want to see anybody in the government get any skin in the game. He says, we in a decade have never seen an RFP, which could be only won if I have security clearance. There's no market. That's their answer.
I think I have one in, I'm sorry, I think I have one in the chat
okay.
as well that I saw. Let me get up here where it says, Here's the question. It says, responsible people agree, national risk, millions of lives. Why do most USG systems run on COTS software? Economics wins?
Well, I'm not a policymaker or a sociologist, so it's hard for me to say why other people do what they do. The observations that people have made is that there are some fairly strong vested interests. The cybersecurity market today is, according to one of the major analysts, $150 billion a year are generated by cybersecurity solutions. These are solutions that don't work. They're penetrate and patch. They require you to do lots of massive surveillance. The emphasis on the government systems are share your results with, tell us what's tax rendered. All of these deal with that penetrate and patch sort of a paradigm. Much of that $150 billion of revenue would go away if people used the Mac controls and a secure operating system. So there's at least incentives not to do that. Notice that the government strategy, their public strategy for secure cyber is primarily one of cheerleading. It doesn't represent the government making an investment. That's what this major vendor said to me. I want to see the government get some skin in the game. No. They simply say, well, we just have to work together. You share your intelligence, we'll share ours. That doesn't address the problem that is being asked. Why don't they use a secure operating system?
It looks like we have a few more here on the chat. The first one that I have says, diagrams such as on slide 23 are built upon x86. What about microcode, errata-type errors, or even memory risk such as rowhammer? Does it make sense to spend the expense on probably secure OS and build upon sand?
No. Many of those attacks you talk about are ones which were considered by the NSA evaluators. And no, you can't use all the capabilities in your intended thing. You talk about the maintenance engine and things like that. Those are because you're running microcode or firmware that you would not run in a secure system. It has to be the case if you take the basic instruction set and you run, and you can provide all the capabilities you need for a PLC or control system without involving those things. Many of those are put there for the typical IT approach to support to penetrate and patch. And so even things like the attacks that you talk about, the hardware attacks you've seen, rowhammer and such, you look at what Google, for example, has said about the defenses of those. They said, oh, well, yeah, the way you can deal with most of that is to actually use a strong process model. But of course, the operating systems we run today don't do that, because for better performance, we want to actually take and put all those multiple things going on simultaneously inside the kernel. And so the hardware provides the capability. Yes, you disable some of the capabilities that are there to support these things. And at the end result, if you look at what GemSauce or any other Class A1 evaluated system, those are not included. Now, what do you lose for that? Well, arguably, you lose some amount of performance. The demonstrated performance impact has never been significant. And yes, you demonstrate some theoretical capabilities that you might want to do. Those capabilities are simply not needed to support what we've seen in PLCs. So yes, you have to use the appropriate part of the hardware. And you can go all the way back to the Pentium. For example, the government actually has had in the past access to the details of the Pentium, and it didn't support many of these things. And yet you can support on a reusable trusted device on a Pentium everything you need to support what we've seen in terms of control systems. So yes, you can't build it on a foundation of sand. You're absolutely right, but you don't have to in order to provide secure control systems.
And we're going to go forward. We have a couple more in the queue still. Next one says, first off, thank you for your talk, sir. My question, does GemSauce offer a standard set of software capabilities, userland software, OpenPLC, et cetera, that are implemented already? Or do companies need to approach ASEC with each time they need to add a capability to integrate into the Secure by Design OS?
So, good question. Recognize that GemSauce is simply an operating system at its interface. So we've talked to several people who are in the control system business, and pretty universally they reflect that they run on top of an operating system. Some of them run on Windows, some of them run a version of embedded Windows, some of them run on Linux. A lot of them, most widely used, is one on produced by Intel for their Wind River, and those are just operating systems. The same PLC capabilities can be implemented. In fact, some of them have actually migrated the operating system just on a different operating system. So from the standpoint of a customer running on GemSauce, they're just running on a different operating system. We have, as a matter of convenience, we provided a Linux source code personality to GemSauce. So that, for example, we've transferred a network file service that is open source Linux. We've run it on top of GemSauce by putting this Linux personality on it and treating it as you would any sort of Linux source code port. So those are things, we make those available as a general Linux. The customers can have that open source interface to that. But in an embedded control system, the major ones we've talked to would in fact probably run directly on the kernel because it's just another operating system to them. So we do not offer a PLC or a network file service or any of those as our products. The people that are in that business know how to build PLCs. We're not good at building PLCs. But we give them a means, they will buy their operating system from somebody else. They don't build their own operating systems. They will typically run on a motherboard that's very typical kind of motherboard. That's what we can provide in a reusable trusted device. They can then do what they do best, build PLCs.
The next one I have in the queue says, I have a lower level question. Does GemSauce run on relatively modern hardware now? I was under the impression that it depends on segment-based memory management, which is disappearing from modern stuff. For example, ARM doesn't have it, x86-64 disables it.
That's right. The x86, again, when Intel was asked about this sort of question, those features of segmentation and protection rings came out of a ARPA project many years ago called Multics. It was asked the question, what do I need in hardware to support security? And their primary result was segmentation and protection rings. I was a consultant to, and others, to Intel when they generated the x86 architecture. They generated it because they thought the world was going to need security. Then the Multics had essentially a spin-off, which became Unix, which became Linux et al. And the whole reason for why they did that is, as at least some of their people said, they didn't want Unix to have to depend on hardware features. Multics said security was more important than particular functionality. And so you went down a path in which they didn't do that. The main Linux proponents have made the comment that the only good thing about segmentation, from their point of view, was that you could turn it off. Well, if you don't care about security, that's true. So yes, you have to make a decision. Is security important for you? Now, in terms of modern hardware, all the current major Intel products do contain the segmentation, do provide the x86 compatibility. And Intel has said that they're committed to do that going forward for the long term. But yes, you have to decide whether security is important. Some of the reasons for disabling, as Linux puts it, the segmentation, are providing things like large address spaces, things like controlling writable stack segments. Those are already provided by segmentation. If I have multiple segments, I don't need 64-bit physical address space. I can get very large physical address space with 64-bit segments if I have a number of them for almost any practical application that we've seen. And the segmentation already had built in it what people do in their memory protect by the fact that you cannot, with a segment, have simultaneous execute permission and write permission to any segment that's there. So if you use segmentation, you get those capabilities that you say you want to have. and you don't have to turn it off. You only need to turn it off if you're trying to provide compatibility with a system that doesn't care about security and therefore wants a flat address space.
And Mike Ficosi, I think I see a hand raised for Chet. Would you open his mic? Must have a question. It looks like your mic's live.
Thank you. My comment, again, with this is you either care about security in the sense of the everything that isn't a D computer, like things that are an A computer, but if you don't care and you will let everything in the market run on a D computer, and I know there are other classifications, but if you're not interested in having the security of an A computer, then it's kind of it's a done deal. If you do care about true security, now you've got a real game, and you've got with the PLC a real solution for once that allows you to take advantage of this fairly simply.
You see, when I wrote the CACM article a couple of years ago, the title was that you could have drastically improved security for where security matters. And my concluding paragraph of that says the first step is you have to decide if security matters. Because if security isn't really critical to you, you probably won't go down this path. I'm not saying replace all the world's computers with this. I'm saying where security matters. And then we've seen a set of experts that says if security matters for the control system.
I think that's all I see right now. Antonio or Mike, is there another question out there that I don't see?
I was wondering if Blaine had a question. I'll open your mic here.
Hi. You were asking Roger kind of what went wrong? Why wasn't this in the marketplace? Why wasn't this technology adopted and pushed forward by the government? Well, in the good old days, there was a guy at the Pentagon named Paul Strassman that Roger knows very well. And Paul decided one day that he was tired of dealing with chasing the rate of commercial development in U.S. government only access or provided machinery. And he says, oh, screw that. We're going to build the rest of the DoD from henceforward is going to build all its IT systems based on COTS technology. And that did not include RFPs for secure solutions. End of game. And most of us who were there at the time remember Paul. Not necessarily fondly.
Well, if there are no further questions, I certainly want to thank you again for giving me the opportunity to share the results we have, and I hope at least stimulate some discussion. Thank you very much for your attention.
Thank you, Roger. We were honored to have you on the agenda, so we appreciate you taking the time to do it.
Thank you, and thank you to all the students asking questions. Okay.
Have a good day.
Bye.
Bye.
Thanks, Roger. Bye.